This presentation summarizes the progress that has been achieved over the last 10 years in the area of full duplex wireless. It includes hardware implementation as well as summary of some of the key patents that have been filed, and majority of them have been granted in the area of full duplex wireless and its applications. Go through some key features of our design. Perhaps the most important distinctive feature of our full duplex setup is the design of a class of antennas called pairwise symmetrical. These antennas result in 40 to 50 dB of isolation by the antenna alone, and this is significantly better than the isolation others have been able to achieve at the antenna level. In addition, unlike methods, for example based on circulators and alike, that are used in other works, the pairwise symmetrical antennas that we use are very wideband and perfectly linear, and these features are critical for the effective functionality of the subsequent stages of the self-interference cancellation. So this concept, which is patented, is applicable to both SISO and MIMO full duplex links. Beyond the antenna, we rely on a nested structure of successive self-interference cancellation loops. The overall structure is designed in a manner that upon the antenna isolation, in any of the subsequent stages of the cancellation in the nested structure, the residual self-interference due to the combination of the earlier stages can be effectively measured and cancelled. And the current design includes all the necessary training signals to achieve this goal. The combination of the first 4 stages results in a self-interference that is above thermal noise level within 1 dB. So we can say that the noise figure of our system using the first 4 technique alone is something below 1 dB. And then there is a 5th stage, which is the long-term digital baseband cancellation, which removes the remaining gap, or a significant part of the remaining gap of 1 dB or 0.5 dB. So here I would like to add a point that the noise figure I'm reporting here is significantly lower than the noise figure in a traditional half duplex link. And the reason is that in full duplex, many of the factors that contribute to the so-called error vector magnitude, various mismatches between oscillators at a transmitter and receiver, various jitters, and so on, in full duplex, these are generated from a transmit unit within the same transceiver and consequently can be better compensated. To continue with our key features, we have patented a number of key applications for full duplex wireless. In particular, full duplex capability enables designing much better and much more effective medium access control as compared to what is used in legacy systems. Many of the shortcomings of the current half duplex links, as it's well known, are due to limitations on the part of the MAC, and the reason is very simple: because devices cannot talk and listen at the same time. This complicates the task of network management, scheduling, and so on, and thereby imposes severe limitations on management of multi-user interference. We have patented a number of techniques to exploit the full duplex capability to enhance the MAC performance, which essentially includes better scheduling, more effective usage of spectrum, and provision for quality of service, better quality of service maintenance. In particular, we have patented the concept of superimposed control signaling, and this is suitable as an entry point for the introduction of full duplex in next generation of Wi-Fi standard. The reason is that the superimposed net control signaling solves many of the problems with legacy Wi-Fi, because now access point can listen to control signals while communicating with the clients that are receiving the service, and this feature can be added such that the access point with this feature is backward compatible with legacy clients. Now, we have also patented a number of other applications for full duplex, including distributed space-time coding, full duplex enhanced security through managed jamming, full duplex MIMO, and a special form of training for full duplex massive MIMO, interference cancellation through relaying, and finally, we have a patent for the application of full duplex to cable modem, and this topic is currently pursued as part of the next generation DOCSIS standard for cable modems. Because as you all know, current cable modems are half duplex, and the issue of spectrum allocation or bandwidth allocation to clients due to this half duplex nature of the current cable modem standard imposes a lot of restrictions on the system ability to service clients in a timely manner, and having the full duplex capability solve many of the issues, and of course on top of all of this doubles the bandwidth efficiency. Next, I would like to spend a few minutes on the implementation. We have implemented the system using entirely low-cost off-the-shelf components. We have OFDM with QAM modulation, up to 64 QAM, and channel coding, of course, all the synchronization, equalization, forward error correction, and so on FPGA. And for the current channel coding that is integrated with the system is convolutional code, but we have designed a much more powerful channel code using coset coding and iterative decoding that is implemented on FPGA, and our intention has been to integrate this with the next generation of our full duplex setup. But that particular channel code is also available on FPGA. So the critical part in full duplex is the synchronization and networking between multiple nodes, because nodes now need to have sufficient time, not too much, sufficient time and an appropriate scheduling to be able to train their own self-interference cancellation channel, and also train the channel to their counterparts for the purpose of regular equalization that we have after the connection is established. So we have developed this. This is one of the points of strength of our system, that this part is developed very effectively, and it's essentially for a point to multi-point setup. Like one node acts as master and has a lot of other nodes that connect to it as slaves, and the role of master and slave, essentially the two nodes are completely symmetrical, but the role of master and slave determines how the training is done and how the data to be sent to those nodes is scheduled, because that's also an important point in full duplex. You want to be sending data to a node that at the same time you have enough data to receive from the same node, and that results in some new way of looking at the scheduling, and we have done that, and we have designed scheduling algorithms that are suitable for full duplex. We have a set of curves showing a typical scenario for the cancellation. The transmit power here is 10 dBm, but it could be higher. The different curves show different stages of the cancellation. For the antenna cancellation, we have something like 36.5 dB. Usually it's higher, but here in this particular test, something has been close to the antenna, most likely. After that, we have an adaptive RF cancellation, which adds another 14 dB. Beyond that, we have an adaptive IF cancellation, which brings another 51 dB cancellation. And finally, we have the short-term baseband cancellation, which here results in 14 dB, 14.3 dB. Overall, these curves show an average of 116.3 dB cancellation. And these two curves that you see here at the end, the purple and the black is the thermal noise, and the purple is what remains after you have removed the self-interference. The difference between these two is about 1 dB in this curve. But there is one more cancellation stage, a long-term digital baseband cancellation, which is not shown here. The effect of this long-term digital baseband cancellation is such that it removes most of the remaining gap to the AWGN level. And the accurate reporting of it would be difficult, because after that we reach to a point that it will be difficult to distinguish that what is the effect of EVM and what is the effect of interference remaining due to the leakage from the transmit to the receiver within the same unit. However, one point I can clarify, that when it comes to that long-term cancellation, although the remaining part is only 1 dB, we see that the system still has a stable linear filter structure to that final stage, and in case that in some situation the difference between these two curves is more than 1 dB, because somebody, for example, stands in front of the antenna or something similar happens, then that final digital stage comes into play. Overall, we have always been able to bring the performance of the full duplex system within 0.5 to at most 1 dB away from the thermal noise level. Here is the hardware setup. This box here contains the FPGA board and the full duplex transceiver, and we have assembled two nodes to talk to each other, and as I said, the design of all circuitry is well documented and all available to be reproduced. We have connected one of the antennas to a vector network analyzer VNA to see its performance. The curves that you see on the right hand side, the top two curves are the radiation efficiency, which is always below -10, which means the antenna at both its ports is radiating efficiently. And this other curve, which is always below -40 dB, is the leakage from one port of this antenna to the other port. Although this antenna is one solid piece of metal, but you see that because of this special design, the isolation between its ports is over a very large bandwidth of 2.4 gigahertz to 2.8 gigahertz is below -40, and over the band that this antenna has been designed for, which is 2.4 gigahertz, the coupling is below indeed -50 dB. Here I have some more examples of the antennas based on that principle of pairwise symmetrical structure that we have designed. Here are examples of antennas for white space application. Here are some more examples of antennas based on pairwise symmetrical structure, and these antennas are designed for Wi-Fi for 2.4 and 5.8 gigahertz band of Wi-Fi. All of these antennas, the coupling between their ports is in the range of -40 to -50 dB. Here I have two other examples of pairwise symmetrical antenna which have been designed for LTE, and this antenna on the left hand side support multiple bands of LTE that are commonly used in North America, and the right hand side is for two of those bands only.